the data science seminar from the University of Washington eScience Institute. Sorry for the little wait. Today, as part of the University of Washington, we acknowledge the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Squamish, Tulalip, and Muckleshoot nations. It is a great pleasure for me to introduce our speaker today, Dr. Brian Henn, who is going to present about correcting coarse-resolution weather and climate models by machine learning from global storm resolving simulations. And that seems to be a timely talk because we just had a big storm. Brian is a machine learning scientist with the Allen Institute climate modeling team. He has worked on weather, flood, and water resources forecasting and modeling for more than a decade, with a particular focus on the climate of the Western United States. Previously, he was a postdoc at Scripps Institution of Oceanography and a data scientist at a Seattle startup. He has a PhD in civil and environmental engineering from the University of Washington. And in his free time, he enjoys going outside with his family on the weekends. Now I would like to invite Brian to continue, and I'm looking forward to your presentation.
Thank you so much, Nicoletta. Thank you for your help in getting me set up here. I'll just start by saying that I work on a group called the AI2 Climate Modeling Group, which was originally the Vulcan Climate Modeling Group, which was spun up in mid-2019 as a partnership with NOAA's Geophysical Fluid Dynamics Laboratory to basically create software to make weather and climate models more faster and more accurate and robust. There are two teams that work in this area. One is focused on making climate models better, or basically more accurate. One is focused on making climate models faster. And I work on the team that is focused on using machine learning to make climate models more robust and more accurate. And we moved from Vulcan to Allen Institute for Artificial Intelligence just about 2 months ago. And I want to acknowledge the really phenomenal team of people that I get to work on, led by Chris Bretherton, emeritus professor at UW, as well as the support from Vulcan and AI2 and GFDL towards this effort. So this is just a GOES satellite image of the bomb cyclone making landfall over Vancouver Island, as well as the really impressive Category 5 atmospheric river sweeping across California earlier this week. And mostly I just put this up as eye candy because I think it's pretty, but it also illustrates that. Yeah, so basically the reason why I show this image is primarily just to illustrate how much structure and pattern there is in the climate system. I mean, you can see all the different things going on at different scales in the cyclone and in the atmospheric river. And as we're thinking about using machine learning in order to improve weather and climate forecast models, it's useful to know that all that structure is there because machine learning in effect is a very advanced pattern recognition system. So all that structure is going to be useful in terms of allowing us to kind of learn different facets of the climate system. So climate models are basically our way of understanding that climate system. And they've done a very good job in general of predicting and estimating the sensitivity of the climate system in terms of temperature to greenhouse gas emissions. And they predict a fairly robust signal in terms of warming for the effects of climate emissions on warming over the Pacific Northwest, shown on the left panel. But in terms of precipitation, they're quite a bit less robust. This ensemble of climate models predicts anywhere from -20 to +20%, or -10 to +20%. Change in precipitation and mean precipitation over the Pacific Northwest, which is quite a bit of uncertainty. A lot of that uncertainty is basically driven by the physical parameterizations that are part of climate models and that are different from model to model. So it's helpful to understand what a parameterization is if you think about the fact that climate models are run across a range of scales. So on the left, I have a coarse GCM running at 300 output from a coarse GCM running at 300 kilometer resolution. And you can see you're really only gonna get the broad features, although they look pretty good, maybe. But this is gonna be quite computationally cheap. And then on the right, you have the outputs from a 3 kilometer resolution global X-shield model from NOAA GFDL that looks, I mean, almost photorealistic, right? You almost can't tell that that is climate model output. This is very expensive and it's run on the NOAA GFDL HPC environment. And but resolves a ton of different features across different scales. So one of the things that we're lucky to have access to as part of our group is basically the ability to run NOAA's global models, both the FV3 GFS model, which is the typical weather forecast model that's run operationally at either 25 or 50 kilometer resolution, or at coarser resolution for longer runs, or as well as the X-Shield model, which is basically a global storm resolving model that produces really fine resolution output like this. So basically our team has the ability to kind of use these models to develop machine learning tools. So what are physical parameterizations? Well, they're essentially tools that are deployed in the model to represent the effects of things that are too small to appear on the model grid. So if you think about that really coarse model, it can't represent a thunderstorm because those grid cells are just too big. And so instead what it does is it runs the parameterization, which estimates the effects in terms of what the thunderstorm would cause in terms of heating and moistening on that grid cell, even though it can't represent the thunderstorm itself. And these are typically run as kind of like bespoke code that are sort of, these algorithms are written into different climate models. And they tend to vary, there's different choices and they vary from model to model. But basically, if the model is too coarse, you need to use more parameterizations in order to account for a lot of the things that the grid itself can't represent. And the way parameterizations tend to work is that they are column local. And what that means is that they operate independently for each column in the global climate model. So they take in inputs, which would be, for example, the humidity, temperature, amount of solar insolation, land surface type or elevation for that column. And then they would predict the heating and moistening rates due to a particular set of physics. So it could be thunderstorms or cloud microphysics or other things for that column. So everything's kind of treated as an input-output problem, which you should naturally think about as being a framing for machine learning as well. So there have been multiple papers and groups interested in this topic over the last few years. Is can we use the advances in machine learning to basically make better physical parameterization predictions inside climate models? Our group is one of a few that's actually operating on a operational real world weather and climate model to try to do this. So that's kind of where our angle is, to try to make improvement. And there's a lot of challenges to trying to do this. For those of you kind of familiar with machine learning, typical machine learning frameworks, right? You have training data, you train your algorithm, you reserve some test data, you do offline validation to see, or you do validation on an out of sample test data set to see how well the model is performing. And for a lot of applications, that might be kind of the end of the development cycle for machine learning. But it's a little bit more complex when you're embedding a machine learning model inside a complex climate model that has a lot of other dynamic components going on. So if you think about the fact that the machine learning might be replacing, say, the parameterization that simulates deep convection or thunderstorms, but everything else is still going on in the model, right? The dynamical core is still running the fluid dynamics solutions and is affecting things around, and all the other physics parameterizations are happening. So that machine learning algorithm is going to operate kind of in an interactive way with the rest of the model, which means that the states that you train the model on might be very different from the states that the machine learning model ends up getting once you start running the model. Because there could be feedbacks basically that are going to run inside the model between the machine learning and all the other components inside the model. So you could think about offline skill, sort of the typical way of evaluating machine learning models, as being a necessary, I guess, but not sufficient criteria for doing a good job in this context. You basically have a lot of other criteria of like, okay, once I actually drop this thing into the climate model, run the simulations for it, does it actually work? And that may not be evident from the offline validation. So we'll see examples of that going forward. So now I'm going to basically take a digression and talk about our computing workflow, because I think it's worth mentioning. I think we've put a lot of thought into, as a team, into getting this working well. So our AI2 climate modeling team, we don't have really access to an HPC computing environment, and certainly not one large enough to run climate models at scale. So we basically do all of our machine learning development in the cloud. And this is accomplished through a few steps. So we have basically the FV3 GFS public release model has been containerized in Docker, and that allows us to run FE3GFS on Google Cloud VM instances. We can do it for fairly coarse resolution. We haven't quite tackled the problem of how to run it across a lot of different nodes for super high resolution modeling, but most of our machine learning training is for the coarse model. And then the other really critical tool that we have for using combining machine learning and FE3GFS, which is written in Fortran, is this idea of wrapping the Fortran model in Python. So we have a tool that Jeremy McGibbon in our group developed that basically wraps the main Fortran routines inside a Python control structure such that you can kind of swap out individual components, either make alterations to model state in between Fortran subroutine calls, or you could replace them entirely with machine learning routines. So basically, we have the ability to kind of mix and match machine learning components with existing Fortran code, such that we kind of preserve most of the, skill that's in the very complex Fortran, dynamical core and initialization systems and all the other parts of the model are sort of preserved, and when we can just sort of tweak the parts that we want to deal with. So at a high level, where does machine learning fit into climate modeling? There's kind of a couple different ways that you could think about doing this. One is emulation. And so emulation would be completely replacing some aspect of the climate model with machine learning. Typically, you would do this for computational reasons to make it faster or more tractable. The other approach would be to try to correct or to improve upon some aspect of the model with machine learning. So that in this case, we might actually be trying to make it more accurate or alter it in some way to produce better forecasts. And then the last part is basically the fact that this is a complex system. We don't really know how it's going to respond. So we're going to make a lot of mistakes, right? So we're going to try something, we're going to change something. It's going to produce worse forecast output. It's going to crash the model. It's going to do something harmful. And so we basically need a rapid development cycle for trying a lot of different ideas to see what we can do to make things better. So I'll talk a little bit about emulation, the sort of first approach of trying to just like mimic a portion of one of the existing physical parameterizations with machine learning. And this has been a focus area of several members on the team: Andre Perkins, Noah Brenowitz, Jacqueline Nugent, who was an intern with us this summer from UW. So the motivation for this is basically to make stable and skillful emulation or mimicry, whatever you want to call it, of the physics component, of a physics component or of all the physics components inside FE3GFS. So if you think about FE3GFS has a dynamical core that solves the fluid dynamics equations, and then it does a lot of different physics, right? It does radiation, it does convection, it does microphysics, it does the land surface model. So you could try to replace any one or all of those things with machine learning. So you might ask, well, what exactly is the point of this, right? If we just are trying to, if we know that there's issues with these physics parameterizations, why would we try to just like mimic it exactly with machine learning? Wouldn't that actually not make any improvement? And really, this is mostly motivated by computational considerations. So most of the growth in computing power is focused on GPUs. And a lot of existing Fortran physics parameterization code, it's really not GPU friendly. It's kind of it's not easily vectorized into sort of the large matrix operations that are optimized for GPU performance. And if, on the other hand, neural networks almost by definition are optimized for this. I mean, they're essentially matrix algebra. And so if you can replace a physical parameterization with basically a sequence of matrix operations, you can potentially speed up some of these parameterizations quite a bit. So, and this kind of goes hand in hand with the team at AI2 Climate Modeling that's focusing on speed improvements for running the models faster. Another reason that you might want to do this is that neural networks are differentiable. You can basically assess the sensitivity of an output to an input or to parameters very easily in a neural network. and they tend to be fairly smooth. They're smooth functions of their inputs. The outputs are smooth functions of the inputs. And all of this has big advantages in terms of data assimilation and in terms of parameter tuning. So basically, it's just a lot more computationally tractable to think about a parameterization as being a sort of simple algebraic function as opposed to a complex sequence of code operations that might be really hard to differentiate or to sort of track the data as it goes through. And then finally, one more reason is that we might want to basically see like what's the upper bound. If we just tried to get machine learning to mimic the model as closely as possible, like how close can we get, right? Like what's the sort of upper bound on machine learning skill to get there? They're all kind of reasons why we might want to do this. Okay, so how does this emulation actually work in practice? So we would run the existing basically run the existing model forward to generate a bunch of output data from that parameterization. So if it was the microphysics parameterization, we'd basically run the model forward, get a bunch of data, a bunch of outputs for what the microphysics parameterization did in terms of changing the model state. And then we would also dump a bunch of model state data to use as predictors. Then we would train machine learning to learn the effect of the microphysics parameterization based on the model state and try to basically come as close as we can to being able to predict the same tendency profiles of vertical profiles of heating and moistening as the original parameterization would do. So the real test is if we swap out the original code with the machine learning emulator, how well does the model run? So we've tried several experiments with this. And basically, this example is replacing the microphysics package with an emulator. And we tried a few different machine learning configurations here. Most of them ended up crashing the model within a few days. One made it to 6 days. And Andre, who's working on this particular problem, was able to basically diagnose that the machine learning emulator was creating negative cloud water tracer concentrations because no constraint had been written in to prevent it from doing that, right? And so the original parameterization would certainly not allow that to happen. Machine learning is sort of a blank slate. If you don't sort of write these constraints in some way, it may not know not to do that. And so after replacing the original ML model with one that had a constraint applied to prevent negative cloud water, we're actually able to get it to run quite a bit longer or it was able to run out at least 10 days, I guess, before there were any issues. And so that's an improvement, but notice that there's still some drift. It doesn't quite mimic the original model in terms of sort of global specific humidity. It's drifting a bit away from the original. These are the cloud water, global average cloud water profiles. And so this is with the emulator on, and this is what the original physics would have predicted. And so they look pretty similar. You can see that the machine learning is picking up the patterns from the original physics, but there's differences between them. So it's a question of, what are your tolerances? I mean, obviously you have to be able to the emulator has to be good enough to let the model run for a long time without developing problems. So that's a criteria. So this is kind of an ongoing issue or an ongoing challenge for us, is to basically to get emulators to work for sort of long timescale runs. And emulation turns out to be a pretty tricky problem, even though it sounds straightforward, right? You know exactly what the model is inputting and outputting, so it seems like you should be able to mimic that with ML. But as it turns out, these physics parameterizations operate at a bunch of different timescales and have different magnitudes of predictions that can be, 0 or very large, depending on, subtle changes in the input state. And so trying to capture this in an emulator is actually quite challenging. And like I said, it has to basically be able to run online. It can't just, you can't just offline verify that you're able to match the original predictions. You have to be able to run in a stable way online, which means that once that emulator starts drifting, once the model state starts drifting a little bit away from where it originally would have been with the original physics, the emulator has to have some ability to sort of pull things back and not allow those errors to just grow arbitrarily large. There has to be some damping of errors in the emulator that could be a bit tricky to make sure that it learns, because it basically has to be in your training data somewhere, otherwise it won't learn it. Okay, so Now I'm going to pivot a bit and talk about the other kind of major approach that we're using ML for in climate models, which is to basically try to make them better by correcting aspects of the parameterizations. So another way of saying this is we're trying to make coarse resolution models run more like fine resolution models without actually running a fine resolution model. The idea is basically, can we use a reference data set to train machine learning, which improves the coarse model's physics? And I would think about this potentially, you can think about this as like the driver assist systems on modern cars. Most of the driving is getting done by the driver, and the car's sort of traditional control systems, right? But there is this assist system that comes into play that can sort of like nudge the car back to where it should be if it senses that there are basically errors in what the car is currently doing. And so we can think about the ML as basically being that system to try to nudge a coarse model, which tends to have large biases and errors if you run it at really coarse resolution, towards the path that looks more like a fine resolution model that resolves more things correctly. If we were able to do this, we would be able to basically get better forecasts for computationally less effort using these sort of ML corrected coarse models. And the way this kind of works in practice is that we are going to nudge the coarse model to a reference data set. And that reference data set could either be observation, so it could be reanalysis data, which is basically just a sort of verified observational data set that represents the atmospheric state all over the globe. Or it could be a fine grid model with the idea that the fine grid model is going to be more accurate than the coarse model. So if you use the fine grid model to train the coarse model will get more accurate. And the idea behind nudging, for those not familiar with this kind of control systems or atmospheric or system model approach, it's actually quite simple. You simply look at the difference between your sort of model that you want to nudge and the fine res and the reference state. So there's basically, you're running a model, you have some other state that you know to be more correct. You want to keep the model you're running on that correct path. So you look at the difference of basically how far away your model is from that correct path, and you establish a tendency in your target model to sort of steer it back towards the correct model. And all that really is, you just look at the difference between their two states, and you divide by some time scale, and you add that as a tendency, or basically a tendency for the coarse model to move in the right direction. So we nudge the coarse model state to the reference state in a training run. So basically, we do this nudging over some period to generate a training data set. So we output all of what those nudging tendencies are. So those are all basically the corrections to get the coarse model to look more like the fine model. And then we try to machine learn those as a function of the coarse model state. So what that means is that the coarse model could learn its own corrections, right? You think this really kind of harkens back to sort of more of a control systems, mechanical engineering kind of way of thinking about things, where a system tries to sort of stay on track by learning the ways to correct itself. So that's the approach. And we've had success with this in a couple of different data sets. So the first one is trying to nudge a coarse model to an observational data set, so to that reanalysis data that I mentioned earlier. So we basically used 2 years of reanalysis data. We nudged the model to the reanalysis data of the first year, saved out all those nudging tendencies, used it to learn a random forest model that basically predicts those nudging tendencies as a function of wherever the model is, whatever the climate state is. And then in the second year, ran the coarse model forward without any nudging, but instead using the machine learning to try and steer it onto a more accurate path. And so we did this to correct temperature, moisture, and wind tendencies. And what we found is that we got improved weather forecast skill for the second year, when we were basically letting it go with its own corrections. We found that we got improved short time scales, we got improved weather forecast skill, And at longer time scales, if you look at the whole sort of year-long average patterns, we got better precipitation and temperature patterns out of the coarse model. And the baseline here is basically running the coarse model with no machine learning correction, right? Just letting it do what it originally would have done. And so we were able to actually improve the precipitation, the magnitude of the precipitation errors in that test year by 23%, which is pretty exciting to be able to basically make the model run more accurately in a forecast mode. And all this is written up in a pretty nice approachable paper that Ollie Wattmeyer in our group got published in GRL this year. So that's a nice introduction to some of our work. The kind of next sort of the last major thing I'll talk about is this idea of nudge to fine, which is the approach I just talked about was nudging to observations, but here we're actually nudging to a different model. So it's like a model learning from a model, right? We have the fine resolution model is the target for the nudging. So we have this 40-day, as I showed the output from earlier, a 40-day 3-kilometer global model that was run at GFDL as part of the Diamonds model and comparison project. And so we can basically use that as our target. And that model is, because it has 3-kilometer resolution, you don't actually need to run a deconvection scheme. It's a fine enough grid that you can actually get thunderstorms occurring on the grid. And so that's an advantage. You don't have to, hopefully you're getting more accurate representation of convection that way. And one challenge with this is that running a global model at 3-kilometer resolution for 40 days produces petabytes of data. So you've got a very large amount of output. And we ended up doing basically a lot of coarsening of that data down to more like 200-kilometer resolution, which is what we run the coarse model at, because ultimately we're doing all these comparisons at the coarse scale. So we needed a way of basically compressing this data down while retaining that signal. So we wrote a lot of code to help coarse grain that really large model output down. And then we ran a nudge training run where FE3 GFS was run at coarse C48 resolution while being nudged to that coarsened fine resolution data over the 40-day period. So that gave us a lot of training data. And I should mention all of this is basically described in a manuscript that's out in preprint right now in James. So one thing that you might care about is, well, is the fine resolution model actually better than the coarse resolution model? Because if it's not, then you're not going to gain anything by trying to machine learn the differences between the two. And you can see in terms of precipitation that yes, the fine resolution model is a lot better than the coarse resolution model. The left panel are the errors in precipitation from the fine resolution model relative to an observational data set, and the right panel are the errors in the coarse resolution model relative to an observational data set. You can see the magnitudes of the errors are quite a bit larger particularly over the tropics in the coarse resolution model, which makes sense because you're relying on a parameterization to represent convection instead of explicitly resolving it on the model grid. So that's a good sign. We have a data set a target data set that is more accurate than the data set we're trying to improve. And now here finally is my first actual machine learning slide. So we ran the nudged coarse model for 40 days and we output the nudging tendencies in the model state every 3 hours over that 40-day period, which gave us a pretty big data set that we could subset into a training data set and a test set. So if you took 130 time steps over those 40 days, and the model at the 200-kilometer resolution has about 13,000 grid cells. So 130 time steps, 13,000 grid cells, that's about 1.8 million column samples that you could use for training. So again, keep in mind that what we're training here is a column. One sample is a column of inputs, of model states as inputs, and then nudging tendencies as outputs. So when we use that for training data, we basically tried several different, being somewhat naive with machine learning, we tried several different configurations of not really knowing what was going to work best. And so we used random forests as one approach and densely connected neural networks as another approach. We did some hyperparameter tuning to try to improve online and offline performance of these models, but that wasn't kind of too much of a focus. But basically, we were able to use that to train these models. And then we had another 700,000 samples that we could use to do offline evaluation. So basically to see, not in a coupled sense, not coupled to the rest of the model, but just in an offline sense, how accurate the ML was able to learn these nudging tendencies. So it's kind of abstract when I say nudging tendencies, like what does that mean? So I think it's helpful to see like what exactly, oh man, that color is really washed up. Okay. Well, trust me, there's some color on the right two panels, but basically the nudging tendencies themselves, this is a transect if you went from kind of the tropical West Atlantic over the Sahara, like north up into the Mediterranean. So looking, vertical transect, looking up into the atmosphere. The left panel are the actual nudging tendencies for what the differences between the fine model and the coarse model look like. So it's basically like what would the coarse model need to do differently to look more like the fine model in terms of moisture. So red would be, add more moisture, blue would be take more moisture out. And so you can see there's actually a pretty complex pattern. It's even more complex when it's not washed out. Positive and negative pattern in terms of like differences between the coarse and fine model. And the machine learning algorithms are basically able to learn as you can tell, a very faded version of the actual data. Yeah, I apologize if you can't see it that well, but basically, if you kind of ran a smoother over the targets, that's kind of what the machine learning is getting at. So at least there's some sense here that the machine learning is kind of learning the right pattern of what to do to the coarse model to make it look more like the fine model. The R² values of the ML schemes in an offline sense are not super impressive. They're only like 0 to 0.4, which doesn't sound like we're doing a very good job of doing prediction. I think a lot of this has to do with the fact that the machine learning doesn't learn a lot of the noisy grid scale structure. There's just a lot of noise in the nudging tendencies that the machine learning doesn't pick up. And I think that's probably a good thing because it probably would be overfitting to the data if it did. We found that the neural networks were slightly more accurate at this than the random forests. I think just due to the way we set them up, there was more capacity to kind of learn patterns in the neural networks. But we also found that oftentimes we would have to regularize the neural networks, which basically means to reduce the magnitudes. For those not familiar with the term in machine learning, is you're basically reducing the strength of the machine learning prediction to make it less noisy. So we had to do that to make the model run stably because we were getting crashes. And I'll show an example of that in a second. So what exactly are these nudging tendencies doing? Well, for the most part, what they're trying to do is they're trying to dry the atmosphere. So the coarse model basically doesn't want to make enough precipitation for the same amount of moisture in the atmosphere relative to the fine model. In order to make enough precipitation, it basically would have to moisten the atmosphere up a lot more than the fine model has. So the nudging tendencies effectively try to just replace that precipitation with nudging. So instead of having to moisten the atmosphere way up to get the right amount of precipitation, the nudging just basically takes the moisture out of the atmosphere, and we consider that the precipitation. So basically that's why there's blue shading everywhere here, is that it's negative moisture nudging tendencies almost everywhere over the globe, where the nudging is basically trying to take moisture out of the atmosphere to supplement the missing precipitation. And the machine learning algorithms, both the random forest and the neural network, are able to learn this pattern pretty well. They're also able to learn it in terms of a vertical profile. So mostly throughout the atmosphere, we're removing moisture and creating precipitation via nudging and machine learning. So ultimately, you end up with a situation where about a third of the precipitation in the original model gets replaced with nudging or machine learning when you try to steer it this way. So, okay, so that's quite a bit of talk about the offline skill, but as I mentioned earlier, that's kind of insufficient to demonstrate that the forecasts are actually going to work. The first kind of the next level up in terms of the hierarchy is when you put this thing into the model, does it actually run or does it crash? And so this is not actually a trivial question. So don't worry too much about all the jittery noise going on the different panels here, but I would just kind of focus on this here. This is basically, the blue is areas where the machine learning is taking moisture out of the atmosphere. The machine learning is basically serving as a proxy for physical precipitation. And you'll see that it's kind of, you can see it's operating on storms and over the tropics. And it looks like everything's going okay, but then you start to notice that some of this precipitation is getting really strong in the Southern Ocean. It kind of keeps growing. And eventually you see these storms start to grow out of the Southern Ocean that are just like physically implausible. Kind of envelops all of Patagonia. Gets bigger and bigger, now it's spreading up the Andes. So this is basically an example of numerical instability in the model where the error growth that the machine learning is introducing is sort of, there's nothing compensating it. And so it's just kind of growing until eventually the model taps out and says, like, these values are unrealistic. I'm going to stop running the model now. So that's something that needs to be avoided, obviously. So we've used basically regularization of the models to try and limit how strongly they can impact things, as well as sort of savvy choices about what their inputs and outputs are to try to avoid some of these feedbacks that we're seeing. So assuming that we have stable models, we can basically then go and compare, we can make forecasts and see how accurate they are. So we chose several different metrics for our forecast skill. The first two are basically weather forecast metrics. So 500 millibar height at days 3 through 7 of the forecast, 850 millibar temperature at days 3 through 7. And then the rest are more like 30-day mean, sort of average pattern, sort of proxies for climate pattern skill of basically how accurate is the precipitation over land, how big are the errors in precipitation and globally, and what are the errors in 200 millibar temperature. And the thing to take away from this table is basically this is the error metrics for just running the model with no ML. And then these are the error metrics for a bunch of different ML configurations. Don't worry about the specifics. Bold is the lowest number, so you want to say low is good. So basically you can see that the best forecasts were coming out of the ML corrected runs. So that's exciting. So we can see that we are getting improvement in both weather and climate timescale metrics from doing ML. Looking, sort of diving a little more specifically in, you can see 500 millibar height on the left and 850 millibar temperature. These are both charts of basically how quickly model error grows with time. And the baseline is this gray, and then the different ML corrected runs are here. So this kind of difference here reflects the fact that the ML is adding somewhere between a few hours to up to a day of forecast lead time skill to the coarse model predictive skill, which is pretty exciting because these improvements in forecast model skill tend to be very incremental. And so adding, several hours up to a day of forecast lead time skill is a pretty good outcome. We get similar performance improvements over the sort of global mean precipitation pattern. You see the error magnitudes are much bigger in the baseline model than they are in either of the two machine learning corrected runs. And we can even learn things like, we can make improvements in things like the diurnal cycle of precipitation over land, which is not something we explicitly targeted the ML to learn. But this gray line here is basically the baseline no ML run. This dashed line is what the fine resolution model does. So this is probably much closer to reality. Basically, you get thunderstorms peaking in the afternoon over land. These are the two ML corrected runs here. So the ML corrected runs are not quite right. They don't quite peak at the right time, but they have a much better amplitude than the original uncorrected coarse model. So it's kind of interesting to see that emerge out of the results. There are some trade-offs here. I mean, basically, some things get worse while other things get better. If we nudge the winds with machine learning to try to make the wind patterns more accurate, we end up with errors in temperature and other places, and we're still trying to tease out exactly why that is. But so basically, some metrics will improve at the expense of others. So it's kind of a challenging optimization problem to try to figure out what the best ML configuration is. Another approach we'd like to kind of push out with this is that right now we're using basically a single 40-day run that's in the present climate to do all our machine learning training. But really what we're interested in is kind of long-term climate model runs where we're able to simulate the climate in the future when greenhouse gas emissions, unfortunately have pushed the climate state into sort of a different position. And so we're running basically different sort of target data sets with like perturbed sea surface temperatures. So colder, same, warmer, much warmer, to try to get a wider range of climates out of which to run these nudge runs and get nudge training data. And this is with the idea that if you used machine learning that's sort of learned from all different range of climates, you'll get a more robust forecast as the climate sort of progresses like through the future. This is an effort that's underway that's kind of being led by Spencer Clark on our team. So we'll wrap up here, but basically machine learning can learn to emulate existing physical parameterizations in climate models, as well as the corrections needed to keep a coarse model on a more accurate path, like observations or like a fine res model. And it can certainly learn it in an offline sense, like we can get good match in the offline between the targets and the machine learning predictions, but that's not the same as online. So there is sort of this additional consideration here of what happens when you couple the machine learning back into the climate modeling system. But nonetheless, the nudge to obs and nudge to fine approaches demonstrate that we can get forecast skill improvements from both the short term out to a month or a year long scales by using kind of careful choices in machine learning configurations to avoid some of these pitfalls of drifts and instabilities. And there's some ongoing long-term challenges that we're trying to address here. I mean, the one that I've really hit on a lot is this idea of generalization. If the training data set doesn't really include enough climate variability to teach the machine learning to know what to do when it starts to get into a different climate state, then it's going to have a problem making an accurate prediction. And so really a lot of our work is thinking about how to generate the right training data set to train these models. We're less focusing on kind of fine tuning the ML hyperparameters as much as we are trying to figure out how do we make a training data set that will actually contain the right information. There's other issues you can run into here. I mean, you can get basically ML learning sort of spurious relationships that aren't causal but show up in the data and that can cause weird things to happen. Like basically learning that the result of a thunderstorm is actually the cause. And so you get thunderstorms kind of happening backwards that can crash the model. So there's issues like that that we have to take some care in making sure that they aren't sort of contaminating our training data. And we want our ML to be both physically consistent and obeying physical constraints and interpretable. And this isn't something that it necessarily will do unless we put some thought into it. There's no guarantee that the machine learning algorithms will say conserve momentum or energy or produce non-negative predictions of scalar quantities or obey Clausius-Clapeyron relationships or all those kinds of things. So we have to think about ways to make sure that it's doing that and that it's interpretable, that we can understand what it's doing physically. So I'll wrap by just saying thanks for your time, and also that there's several papers out there now that we've published or are in the process or are available as preprints. Additionally, we've had put quite a bit of effort into making sure that our code is open source and available. And so our repo is up on AI2CM on GitHub, or our various repos are under that index page. And our climate page, our team page is up as well, and my email is there also. But thanks so much. I'll take your questions.
Thank you very much, Brian. Please ask Brian questions. Brian, you also have some questions in the Q&A.
Okay.
We can take them directly from there while you're thinking about other questions.
Oh, sorry.
Yeah.
Okay. So Bart asks, in all of your training and the testing data based on model, is all of it based on model output, or are there cases in which you use observation as well? So yeah, that's a good question. So basically the case where we nudge the model to observations, I mean, that's kind of basically just saying, that's a proxy for observations, right? We're saying that the nudging is trying to make it look like observation. So in that case, yes, we're using observational data, reanalysis data as training data. In the nudge to find case, we're using basically a model training another model. So there's no observations involved. You just kind of hope that the fine resolution model is more closer to the truth than the coarse model. So Andy Berner asks, is there any theory as to why the Amazon was biased dry in the ML corrected framework? So yeah, we get some interesting patterns in terms of where the ML tends to put moisture. We have this issue where the ML tends to, it's hard to see on, I guess it's easier to see on Zoom, but the ML tends to put like light pink everywhere. So if you know what happens when you try to fit a regression model to noisy data, you end up with a lot of kind of mushy predictions in the middle that aren't like very confident either way. And so we end up with this issue of frequently having kind of like drizzle coming out of the machine learning models where it doesn't really know where to put the precipitation. And so it kind of like puts light precipitation all over. That's something that might be a result that might be causing that. I mean, you can see that there is quite a bit of wet bias over sort of the Amazon Andes boundary. And I don't have a good reason as to why specifically that's happening, but it may be related to that. Oh, and so maybe I'm actually looking at the wrong figure. I think Andy was saying it's looking at the nudge to obs case. Yeah, again, I'm not entirely sure. This is a challenging. This gets into basically the challenge of interpretability. Like the machine learning is going to make predictions, and then trying to disentangle exactly why it made that prediction is challenging because the prediction doesn't really occur in a vacuum. It occurs in basically the interaction between the machine learning and the rest of the model. And so, yeah, unfortunately, I don't have a better answer to that, but it may have to do with basically like shifting the fact that the machine learning kind of shifted precipitation to sort of different areas. It's, moving it more out of the Amazon and into more of the Andes or in the sort of Central American coastal ocean. Great.
We're past time, so if you don't have other questions, wrap it up here. Thank you, Brian, again, for delivering this really interesting talk today. And we hope to host you again sometime soon.
Thank you.
Thank you.
Thanks, Em.